Okay, so let's look at chapter 11. This one will start off as a hot mess, but it's how we actually look at these guys from a physical chemistry standpoint, which is quite painful, honestly. There's going to be a lot of word jumble at first, but eventually we'll get to some we know. We'll get there eventually. So let's look at just a standard dissolution of zinc into zinc solution to what's actually occurring as the metal slowly dissolves. Now, if we put a zinc electrode and partially immerse it in an aqueous zinc solution, as zinc dissolves, we're going to see electrons donating into the metal and zinc going into solution, where we see a small negative charge buildup on the metal and a small positive charge buildup in solution. Now, while there's very little zinc actually dissolves, there's enough to create a electrical potential about 1 volt. While this does not change the charge of the metal by much, it does change the charge of the solution based on what we just saw about electrolytes in solution. Just adding a little bit of these guys in there is going to create a big effect because that is electrostatic interactions. So looking at this, looking at what's actually going on, there's going to be work that's going to be done. That it takes work to reversibly transfer so many moles of a charged ion from a chemically uniform phase metal at one electrical potential to another. Otherwise, you would have identical phases at different potentials. You would have to move this around, or else you can't have the same thing with different potentials within the metal. There has to be like some sort of differentiation. Now this work is going to be the sum. What is going to be the change in the work is going to be the difference between this electrical potential phi, the two things times the change in charge Q. Q is our negative number of electrons times Faraday's constant times the change in moles of the total number of charged ions. And of course, Faraday's constant is the number of electrons times Avogadro's number, which gets us the electrons into electron moles, or moles of electrons. Now, because this is on non-expansion work, where Gibbs is related, the change in Gibbs is related to the change in work. There will be a difference in the electrochemical potential. So there's going to be mu hat, which is different from our standard mu. We can say that, well, the change in our Gibbs is our mu hat 2 times the change in moles minus the mu hat 1 change in moles. But we can say that, well, the electrochemical potential differs from the chemical potential by a factor of Z by F. So the chemical potential plus the effective charge, number of electrons, constant, and a electrical potential within this situation, such that as the electrical potential approaches 0, the electrochemical potential will be same as the chemical potential in this situation. So no electrical potential difference means we're no difference in the electrochemical potentials. So now looking at that, back at that change in electrochemical potential, we can say mu hat 2 minus mu hat 1 is going to equal to the change in electrons. That's going to be constant. Mu 2 minus phi 2 minus phi 1. So the difference in electrical potentials times Faraday's. Now we can only measure the difference between these two potentials. We cannot measure just one by itself. So we're going to set one equal to 0 and the other, and measure the other off of that. The same way we measured the Gibbs solvation of one ion in relation to another, where we set hydrogen as being 0. If that's 0, if 1 is 0, we can simplify that and set mu hat 2 and get mu hat 1 to the other side. How does mu hat 1 and mu hat 2 differ? They differ by the potential between the two. So saying that particles in normally identical phases will have different electrochemical potentials if there's an electrical potential held between them. So particles will also flow to seek a minimum electrochemical potential. So negative atoms will be moved towards a more positive ECP, new EP, and more positive atoms will move towards the less positive potentials. So it's that delta G is going to be the sum of all of our ECPs, but that also has to equal 0 for all electrochemical reactions. So the mu hat is much more easily controlled than a traditional mu, because we can actually measure and vary our chemical potential, our electrical potentials, by running various circuitry, as we're going to see in a little bit. We run various circuitry, we can change the potential. But before we get to there, we have to look at how do we look at cells, the conventional and standard states. So to consider these things, we need to understand an electrochemical cell. Now, Volta and Galvani are well known for first discovering the battery. It was John Frederick Daniel who first created the first practical battery, as we see above. He used much the same active materials as Volta, using the copper sulfate, and zinc sulfate, and sulfuric acid medium. But he was the first to come up with the idea of separating the two electrodes into two different cells, each with their own electrolyte, so not putting them in the same cell. However, these, in order for the circuit to be complete, he had to connect them by either a semi-permeable membrane or a salt bridge. Now, looking at the traditional version of the Daniell cell, we see the zinc electrode submerged in zinc solution, the copper electrode submerged in copper solution, salt-rich KCl bridge, and electrode running through there with a voltameter. So we can read the chemical potential between the two. We write anode on the left, the cathode on the right. Okay, so let's think of that cell. Let's talk about potential. Each half cell will have a difference in the electrical potential between the metal and solution, thus why it flows from one way to another. Now, would it be possible to measure this electrical potential of a half cell by putting a platinum wire, which is unreactive, dipping it in solution and dipping on the electrode to complete a circuit? And it's like, well, the potential difference measured between the wire and electrode and wire and solution, could we measure it from there? Now, the difference in the electrical potential can only be measured between one phase and a second phase of identical composition. So we can't quite measure it by putting a wire between those two. So we can only really measure the metal to metal. So for this reason, the standard state for all ions in solution, the chemical potential of solution is 0. So we can simply say that we can't quite measure the electrical potential of a solution. So we can simply say that all the electrochemical potential of the solution is just the chemical potential, period. And because we last chapter learned how to measure the chemical potential of this electrolytic solution, we can calculate this using the Debye-Huckel equation. So that can be dealt with. Well, so now we need to consider the electrode. Now, the electrode is normally a neutral metal, so the electrochemical potential of this is actually just the chemical potential. It's mostly neutral, so we just say they're the same. But metals also sees a dissociation of electrons and cations. So the chemical potential of this metal is also going to, what it sees is, well, the charge of electrons times the electrical chemical potential of the electron plus the electrical potential, chemical potential of the cations formed. Now, for an electron, it's not possible to determine the chemical potential of the electron. So the standard state convention is just, oh, so there's no chemical potential, so it's just 1 times phi times F. And for a cation, it's going to be chemical potential of the cation plus Z phi F, because we said this was related by chemical potential Z phi F. Now, if I put those two together, and the chemical potential of the metal becomes Z phi F plus chemical potential of cation plus Z phi F, positive Z phi F. Those two cancel out, and we say the chemical potential of the metal is just chemical potential of the cation. Now, how we set this up, if we say this is done at standard pressure and standard temperature, these guys are going to be 0 for a pure element in its standard state. Say chemical potential is 0 for a pure element in standard state, so this has to be 0 for a pure element at its standard state. But if we substitute this last equation part into the top part, we'll get that that these two are equal. These two are equal, and over here, we can say the chemical potential of the cation is negative Z beta F, which is this guy, the ECP of the electron, plus the electrical chemical potential of the cation. And at standard state, it's just going to be the standard state, the chemical potential of the metal cation 0, and so that the electrical chemical potential of the metal cation is equal to the charge chemical potential in Faraday's. So saying that at standard state, the ECP of the cation is times the number of electrons transferred times a constant times the chemical potential, which we can measure. Now, while all this is very difficult to measure for an individual potential, it is still possible to measure that for a chemical potential. But rather than try to measure an absolute electrical chemical potential for 1/2 cell, it's much easier, much more convenient to measure the difference between two cells together. And once again, this is best done from a fixed reference point. When we measure a relative potential from fixed reference, we can get the other one with some ease. We're going to set the standard hydrogen electrode, SHE, as our reference, arbitrarily setting this to 0. We've set hydrogen to 0 for a lot of things. Why stop now? So for this given reaction, H plus and 1 electron goes to 1/2 mole of hydrogen gas. You can say that, well, for this reaction, the chemical potential of hydrogen cation plus the electrochemical potential of the electrons equals 1/2 times the chemical potential of the hydrogen gas, due to this being neutral and aqueous species. Now, if we try to account for a real solution, the hydrogen part goes to H naught H plus, or say mu naught H plus, RT ln activity of hydrogen, minus Faraday phi. We can cut out the Z because it's 1 electron, times 1/2 mu naught H2 plus 1/2 RT ln fugacity. And then if we then try to solve for the cell potential of this guy, say cell potential is mu naught for H plus minus 1/2 mu naught H2. over F minus RT F ln fugacity to 1/2 activity to activity. Now this first whole term, the knots go to 0 due to our standard state conventions that for a pure element in its standard state, we set those to 0. So those whole terms drop out. We're left with RT F over ln fugacity over activity. But if we consider this an ideal dilute solution, and what like activity goes to essentially 1, and we consider this is like an ideal gas, or essentially a significantly dilute enough gas, then fugacity goes to 1, and natural log of 1 goes to 0. So that essentially the chemical potential at standard state conditions are 0 for the standard hydrogen electrode. A lot of hoops to jump through. Here's where we get to finally the reversible cell potential, how we can measure this. Now, cell potential measured under reversible conditions are directly related to the 3 major state functions H, S, and G. That the reversible cell potential is essentially the electromotive force, and that can be determined by the following experiment. We set a cathodic wire connected to a slider along a slide wire resistor, as we see here, where the resistance is a function of the distance along the resistor. Now, the left potential is held constant, while the right is a variable due to this potentiometer opposing the cell. We have this potentiometer up here and this resistance. At a certain part along this slide wire, the right potential can be adjusted to equal the left, making the left and right equal. And if the left potential and the right potential are equal, no current will flow through this cell. Thus, this position can be noted, and it can be used to determine the electromotive force, because this guy, the potential up top is constant. And if we note how far this is, we can figure out where's the point where they cancel out. Now, if I move this to the left, if we left a little, the right potential would increase. Cell will flow clockwise in a spontaneous direction. If I move it to the right a bit, the right potential will decrease, and the cell will flow in a reverse reaction. In this way, we can establish our reversibility and determine our cell potential. So, where we're going to stop for now, and we're going to next video, we're going to look at actual chemical reactions and not all this hypothetical nonsense.